Hello, my name is Matthew Landis, and this is my Lab 1 presentation on charge tapes. In this lab, we observed many fundamental physics principles. We saw the force of gravity constantly pulling the tapes downwards. We saw the electrical force causing our charged tape sheets to repel. The on-screen formulas were all used in this lab. Their uses are mostly self-evident, like calculating the force of an electron from the electrical field and solving for gravity. However, I also included the position and velocity update formulas, which are derived from Newton's laws, as they allowed me to demonstrate any motion of the digital floating tape. This lab worked by using static interactions to place a non-zero charge on the strips of tape when they are pulled apart. Because of their charge, they now repel each other, allowing us to determine the charge on each. We do this by moving the tapes together until the force against each other is just enough to be able to lift the top tape out. We measure this point because this is just past where the net force on the floating tape is zero, as the electrical force is canceling out the force of gravity. Because charge is part of the electrical force formula, it is as seen here. We can use algebra to solve for this unknown. On screen now is some of the code I used to model the interaction from the lab. At each time interval, the code solves for the gravitational and electrical forces and combines them to solve for the net force of the floating tape. This can then be combined with the position and velocity update formulas to allow the particle to oscillate slightly while experiencing a nearly net zero force. I've provided a link to my code on this slide and as part of my submission. You can see here where I have the charge that is demonstrated at where they're floating at the set distance of 5.8 centimeters apart, starting at 0 and 0.058 meters. Here is my loop that runs for 10 seconds, demonstrating any motion that would occur between the two charged particles. And then here is my formula or method that calculates the force. In order to create my model, I had to make some assumptions. These included neglecting air resistance, treating charged tapes as point charges. That last assumption can be made by assuming that the two tapes have equal, evenly distributed charges. The completed model shows that the electrical charges for both tapes are approximately 2.4 times 10 to the negative 8 coulombs. This is demonstrated by the fact that the particle does not move more than basic oscillation, meaning that the forces are nearly perfectly balanced. Also, part of the movement can be attributed to the result of approximations due to time interval delta t. After completing the experimental portion of the lab, I've determined that the charge of the statically or electrically charged tape is consistently the same sign, and that sign can be found to be positive using an object of known charge for reference. My tape was positively charged because it was shown to attract the negatively charged pen after rubbing this pen against a cloth, which is again known to be negative. I then would also use the maximum distance that would cause the top tape to float to calculate the electrical charge to tapes by setting the electrical force equal to the gravitational force experienced by the floating tape. Hypothetically, what if we were able to instantly flip the charges of both electrons and protons, making protons negative and electrons positive? If this were to happen, there would be no way to observe this change. If we were able to actually see the electrical fields themselves, then we would see them flip direction. However, because we can only observe their effects, we would be absolutely unaware of this change, as all interactions are only the result of the positive and negative relationship. As long as that is preserved, with like charges repelling and positive charges attracting, there would be no visible or known effect. When replicating this experiment, it is extremely necessary to touch the charged tape as little as possible, because the tapes are only able to repel each other and allow the free tape to float by having a non-zero charge with the same sign on both tapes. When you touch the tape, especially the non-folded portion, some of the charge stored on the tape can float into your body as your body has a nearly zero charge. This has the potential of reducing the floating distance, making the tapes unbalanced in their charge, or simply making them not repel each other at all. This transfer of charge from the tape to you is the result of the charges attempting to equalize and redistribute themselves as a result of the repelling forces between the electrons on the tape. Thank you.